All right, so welcome back to the afternoon session of this symposium. So we have lined up a series of 3 talks, right? First one by Associate Professor Vincent Tan from the Department of Electrical and Computer Engineering, and as well as Department of Mathematics, right? He's going to share his insights and vignettes from teaching the theory of machine learning, right, to math majors. Yeah, Prof. Tan, please.
Thank you very much for the kind introduction, and thank you very much for having me here. I want to thank Colin and the organizers for giving me the chance to speak about my experience teaching the theory of machine learning to mathematics majors. So there are many courses on machine learning and data science on campus. So I want to share with you a unique perspective from my experience in teaching the theory of machine learning over the course of about 5 to 6 years since this course at the math department was started. I want to motivate why we care about theory by parameter tuning. Okay, so this is something that we often, or practitioners often do when they are faced with a particular machine learning problem. They choose a particular algorithm, and the particular algorithm in it will have hyperparameters to tune. So here we see a particular person who is trying to use the so-called 0-1 loss to classify the red points. I guess the color has all been gone, is it? Or I cannot see it from here. To classify the plus points from the star points, okay? So however, the 0-1 loss is probably not appropriate in this particular setting. So he tries to fiddle with it. He tries to fiddle with it by adding some sort of parameter here, which has been contorted, I guess. Oh no, the equations have been contorted. Initially, my slides, they were okay. So the point is that here some parameter has been included, and so the practitioner is trying to tune it, but he still gets very confused. He doesn't know why it is not working, because all that it is doing, all that the epsilon here it was supposed to be doing, is simply to scale the weights of the particular classifier, which is not doing what it's supposed to do. So he still gets a very large generalization error, which is very unfortunate. So he comes to take my class, and I tell him the right thing to do is to look at the margin, all right? So in order to look at the margin, you need to then understand what is the purpose of doing so, because understanding the role of the margin will help you to generalize well. And so he finally learns this contorted equation here, which is not meant to be, but he finally learns the support vector machine, and he finally sees that, well, that's the right thing to do. So learning the theory of machine learning can actually help you to bypass all the difficulties in doing parameter tuning. Of course, it's still a little bit of parameter tuning, and wise parameter tuning is still necessary for you to achieve your goals. But the purpose of my module is actually to do this in a systematic and theoretical manner. Okay, so I mentioned that there are many modules on machine learning and data science on campus, and a quick search yields all these results. So is there a role for yet another machine learning class? Okay, this is machine learning, and this is what I found for data science. Okay, so here comes my module. This module has been taught for, well, I guess 6 to 7 years now, and it is a 4th year module in the math department. In which I have a minority appointment at. So it teaches the theory of machine learning, although the title does not reflect it. It is alternate between Jonathan Scarlett from the School of Computing and myself. And of course, whatever I say applies to a particular group of students who may be mathematically inclined. So the material here may not be universally applicable to every student on campus. So this is a particular class that is maybe catered towards students with a rather strong mathematical background from their 1st, 2nd, and 3rd years. So the clientele include actually pure and applied maths majors, DSA, that's the data science and analytics students, of which there are many in the Faculty of Science. We have many students from the double degree maths and CS, as well as a sprinkling of students from all over the place, like engineering, Faculty of Arts and Social Sciences, and so on. Okay, so the prerequisites for our class include numerical analysis, algebra, linear algebra, as well as probability, all at the MA2, MA3 level. So serious math. Okay, so we have a focus on theory, and the implementation part is very, very minimal. Okay, so while students are required to use some programming languages to implement what they learn in practice, this is kept to a bare minimum. All right, so the first thing I talk to them about is, what are we trying to do? All right, the first thing we learn is binary classification, which, as you know, can be motivated from this cat and dog type of example. And we would like to learn, say, a linear classifier. The first theorem they learn, okay, is the so-called perceptron convergence theorem that I will illustrate here. So here we have two types of images, one containing dogs and another containing cats. And of course, what we would like to do is to devise or learn a function f such that, given a new image, we can say that it contains a cat or a dog. So this is meant to be a function bracket picture of a dog spitting out a dog, and a function bracket cat spitting out the label cat. Okay, so we have not seen these images before, but we would like to learn such a function. So how do we do that in an abstract and mathematical way? So the way we set this up, of course, is in a traditional manner. But the first thing that we are going to learn, as I mentioned, is the so-called perceptron convergence theorem. So here we are given a labeled training set. Each of these is a vector of the same length. Okay, so these are basically images that you can think of them as being vectorized. Okay, so each of these training vectors has a certain binary label, all right, which is a yt between which is plus or minus 1. And given a particular labeled data set, we would like to find a function that outputs -1 or +1, such that it outputs and it predicts well on unseen images. So this is the standard binary classification task. To keep things simple at the very first round, we basically want to learn a line, all right? So that's a linear classifier, such that a line is basically characterized by its normal vector. Here is the theta. And we want the inner product between this theta vector and the feature vector x to be positive for all positively labeled samples and negative for all negatively labeled samples. So here, basically, we are restricting to basically a linear function that is then thresholded. Okay, so the whole point is to learn a particular theta here, parameter, such that we have these desirable properties that the inner product is positive for all positively labeled samples and negative for all negatively labeled samples. And the key, the first thing I teach them is the so-called perceptron theorem, which is a 1950s thing, 1950s technology. But it then motivates the notion of margin, which we can then talk about in the theory of support vector machines and so on. Okay, so this is nothing but the perceptron algorithm. Basically, if you classified a particular point wrongly, then you add on label multiplied by the point to your parameter vector. Okay, and so I motivate this algorithm and I tell them that actually it works well, okay, but don't trust my word for it because we can prove something about it, okay? So this was discovered, I tell them, by Rosenblatt in the 1950s, and that was the first implementation of the perceptron. And this is as I mentioned, this is the very first thing that I proved to them, okay? And they are meant to know it, and they are meant to apply it in different particular settings, okay? So we can tweak the setting a little bit. And to show them that actually this works, I also program this out and tell them that under some conditions this works. If some conditions there are violated, it may not work. For example, if we have infinitely many points, all right? Then some of these conditions may not be fulfilled, because if you've got infinitely many points, the first condition there may diverge. There may not be any bound. All right. So students are very intrigued by these sort of things. Because why? Because these math students in the first, second year, third year, they learn convergence results from analysis, from linear algebra, and so on. So they see a very cool application of all these convergence theorems to a cat-dog classification problem. Okay, of course, this is very abstract, and of course, when we do cat-dog classification, we never use this sort of algorithm. But nevertheless, this gives them an idea that what they have actually learned in their pure math classes can actually be used to good effect. Okay, so that is basically my first couple of lectures summarized. So on the left-hand side here, we have the sequence of topics that I go through, from single layer perceptrons to support vector machines to kernels to boosting mixture models, and finally graphical models, which are probability distributions defined on graphs. Associated to each of these topics is a major theorem that I expect the students to know how to prove, to reproduce, as well as to innovate on. So I will change the setting a little bit, and they are supposed to prove something interesting, as I will show you later on. Okay, so we want the learning to come full circle. This is a class at the 4th year level. So students in the math department would have taken analysis, algebra, optimization in the 3rd year, probability in the 2nd year, linear algebra in the 1st or the 2nd year. So all these come together very nicely to show them that whatever they have learned is not just abstract, but can be applied to a real world setting. And this really shows them that whatever package they use later on, like NumPy or some sort of machine learning package, well, there is underlying mathematics that underlies all of it. Okay, so you probably cannot see all this math here, but they were meant to be rendered properly. So I also set assessments that challenge. Okay, so as I mentioned, every topic there is a main theorem. So I don't want people to regurgitate. Okay, that is not the point of learning. But I want them to learn how to apply that to different settings. So this is meant to be a very cool problem that I designed. So here what I'm trying to say is that, okay, I teach convergence theorem in boosting, all right? And in particular, the AdaBoost algorithm. I show them that the training error actually converges to 0 exponentially fast. And the test error actually also converges nicely. And this is a result actually by your head of department, Lee Wee-san, when he was a PhD student. So, well, all those theory is very beautiful, but it's only applied to the binary setting. Can you change your algorithm so that it actually applies to the multi-class setting as well? What sort of tweaks do you need? So here, the only tweak that you need, and these were shown by these researchers about 10 years ago, Joe Rossett and Trevor Hasty, you need to add this log k minus 1 here. Why do we need to add this here? So I guide the students through it, and they find it very exciting. That actually whatever they can learn, they can innovate, and they can prove something non-trivial. Okay. All right. So students are very intrigued. The good ones, I identify them. Basically, I steal them from the crop, and then I ask them to do FYP with me. And so we can actually do a lot of cool things together. Not only experiments, but also theory. So, for example, Ruixia was a student in my class in 2017-18, and she did something on matrix factorization applied to sports analytics. So this was many years ago, 4 or 5 years ago. So, right. So I get some very interesting comments at the end of the semester. So this student said, coming from an algorithms background, he or she finds that algorithms are well grounded in proofs. Machine learning, on the other hand, always seems like rubbish to me, because people often tune parameters and it works well, and they give themselves a pat on the back, and there isn't a really good reason why. This module changed my perspective on that. Thanks. And I mentioned to you this tennis example on the previous slide that one of my students worked on. So in the previous offering, in the last offering of it, I mentioned this particular example to motivate the so-called expectation maximization algorithm, which is a very key component of machine learning in my class. So I'm able to use that to motivate why we actually want to learn the expectation maximization algorithm. I mentioned this student's project, and that really made people excited. So some people say that they have learned a lot more from me than other ML modules combined. Anyway, so this is just a short sharing session for me to tell you about my experiences teaching this machine learning class to math majors. Math majors have a particular background, so you must cater to them to make them intellectually challenged. Otherwise, they'll be bored. So programming is at a minimal in my class. So they need to learn how to they need to learn the basic proofs, and I ask them to do a little bit more advanced proofs. Okay, so thank you very much for your kind attention.
Thank you, Vincent. We have one question from Padlet. It's from Prof. Tucker Kellogg. I will just read verbatim. Vincent, your class has a focus on complex analysis, but you don't have a prerequisite of real analysis. How do you bridge that gap with the prerequisites you do have?
Oh, okay. So first and foremost, the class does not require complex analysis. Complex analysis is a different thing. It's like contour integration and things like that. We don't really require that. And all students who come to this class will have analysis. We don't need to say that there is a prerequisite, because all students have to go through the basic analysis class in order to come to 4th year. So we can assume that students know a little bit about convergence of series, sequences, functions, and things like that. So if they don't, they're in the wrong place.
Are there any other questions from the floor? I don't think we can take questions. We don't have other questions from Padlet. Yes. Thank you very much then, Prof. Vincent Tan. So next, we have our very own Dr. Ganesh Iyer, Department of Computer Science. He will speak to us on the essential software engineering skills for artificial intelligence and data science. Dr. Ganesh, please.
Thank you. With your permission, I am just taking off my mask, otherwise it's blocking my class. First of all, let me thank Colin and the organizing team for selecting me to come and speak here. I have joined NUS very recently. I am also an alumni of NUS. I did my master's and PhD from here. So as a faculty joining back very recently, and then this is probably my first event where I get to meet a lot of you. So thank you very much. And since I am also new, I thought I will just give you a very quick introduction about myself. So apart from my master's and PhD from NUS, I have been working in industry for a lot of time, and the last company being Salesforce as a DevOps engineer. And then I have handled a lot of roles in the industry, including a manager, architect, and different roles and titles. And I was fortunate enough to get an opportunity to give a lot of talks. So talks is something that always excites me because it's a place where we get to know each other. We meet new people. And all these pictures that you see are a traditional Indian dance where it is me. So I perform that dance. I'm very passionate about it. Also, most of my free time and whatever that I can contribute to the dance, I always do. So yeah, some of them are taken in Singapore also. This is taken in Singapore, and some of them, yeah, while I was doing my studies. Okay, so after lunch, I know it is a bit challenging time for me to grab attention of you guys. So I thought I will start with building a house. It's pretty straightforward, right? Building a house is all about a few steps that you start saving money and then plan where do you want to build a house or all the things. And then start thinking about number of rooms, where the garage should be or whatever. And then the design of the house, how do you want the house to be designed? And then the actual construction and so on and so forth. And then it comes to a place where you start living, and then you see that, okay, there is a problem. Something is not working. Then you call the guy who come and just do some magic, and then it works. So this is how we build a house. Now, what is there for building a house to our symposium? Yeah, so if you see, software engineering is essentially similar. You start planning. I mean, any software that you develop or any project that you work on always starts with a planning. And then once you plan, you do your analysis, you understand the requirements well, and then you start designing how you want it to be. And then once you design how you want it to be, you actually start developing it. And then you test whether things are working well. Is the door functioning properly? I had this nice incident at my previous house, which I own. It was a ready-made house that I bought. Everything was already fit. And then I went to open a window. I understood that I'm not able to open that window. because the window, the iron grill that supports the window and the window itself were stuck because of lack of testing, no integration testing. They independently developed their product, fixed and went back. And it's only on production where I just entered the house, and on one fine day after a few weeks, I wanted to open that window, I can't open. And then I had to fix it. I had to really take out that piece of iron and then do some modification. So testing and then moving in and then finally maintenance. So it's essentially the same thing in case of software engineering. Now, there are multiple ways of doing it. So two major ways are, one is our waterfall model. It looks like a waterfall, a nice waterfall, where you do each step one by one. You probably don't go back. You won't go back to the previous stage, most likely. The other one is more probably trendy, where you see that your Gmail or your Facebook, when you open on next day, suddenly a new feature pops up. You don't even see that the system went down, but there's a new feature. And again, after a few days, or again a new feature comes up. It's completely incremental. At any point of time, you have a working model which is which is getting improved. The iteration over iteration. So that is generally iterative model, and agile is one of such very commonly called model. Now, when it comes to our context, the machine learning or artificial intelligence, here for my rest of this session, I will be taking up machine learning as a representative from the entire AI space. So is machine learning, for example, is just building a model? Essentially, I know all of you agree that it is not. It is not just making a model, right? So it is a lot of steps, a series of steps that we do, right from okay, I have this problem. Now I want to first understand how do I get data from? Where do I get data from? And then once I get data, there will be a lot of missing things, a lot of manipulation that I have to do. And we often agree, I'm sure all of you agree that majority of our time on a machine learning problem is focusing on the data preprocessing. Cleaning up and making sure the data is ready. And then comes the whole mathematics that Professor Vincent just spoke about. The model itself is another challenging area, the model itself. And then potentially what I want to bring it here is, after that, there are a lot more when you want to do it at an enterprise level. Once you agree that this is a model, it is trained, some of the unique challenges that I can correlate with software engineering is the deployment. Where do you run it? And then how do you factor improvements? How do you get feedback? How do you improve? So the whole deployment itself is also very important. And then comes at an enterprise level, any product that you deploy comes with a lot of monitoring, logging, all those site reliability engineering principles. So essentially, this is my motivation for this session, where we tend to focus probably on a lot of the initial stages until we build and confirm a model. I would say when it comes to an enterprise level project, or where you want to use this in live for masses, it's also extremely important that the deployment and then the after part, the maintenance, the monitoring, understanding the issues is equally important. So from this very basic context, some of the key takeaways. One is AI also needs to be agile AI, where you actually go through different steps of planning, design, building, testing, and then, okay, you deploy it. And now you start seeing there's a problem. For example, one of the speakers in the morning said about this unique challenge that Amazon had on hiring and ending up hiring only male candidates. So the moment you see that, potentially you can then take it to the next sprint. You can add that into your system and then improve and then redeploy. So you always have a product that is running and then it is getting improved. So, and this whole thing needs the entire software engineering lifecycle or the system development lifecycle implemented even for a machine learning project. And as equal is the ops part, the operations part. So if you see a typical DevOps, or here I put even a little bit of security also, the DevSecOps, you see a lot of stages on the operations part, where the moment you develop the system, how do you test, how do you run your regression test or smoke test and other various types of things, and then how does it get deployed, everything gets automated in the context of an IT. So at Salesforce, where I worked, I used to work in this ops part. And then we used to have 40,000 virtual machines running in the cloud, and not just one cloud, multiple enterprise clouds. And then that needs to take care of, I mean, what if suddenly a natural disaster comes, and then probably if you depend on just one cloud and one region of the world, and if something happens, how do you do business continuity? So keeping that in mind, they have multiple clouds. They have agreements with Google, Amazon, or whoever, a lot of them. And then we used to take care of having our product running on many of them, and then making sure that the system can, in case one of them is shut down immediately, the other one can continue give business to the customers. And Salesforce, for example, being a huge enterprise company with such a huge customer base all over the world, they can't afford to lose even a second. So, and you can easily map that into our ML ops context, where you have to follow similar pattern. This monitoring, for example, is extremely important. So in Salesforce, we have multiple dedicated teams who does different levels of system monitoring, site reliability engineering teams. And what I want to also tell is many of these have ready-made tools or ready-made toolkits available. Companies who offer those services, with many of them even being open source. So we probably need not build any of them from scratch. We will be able to even leverage some of these existing enterprise level tools that are available. So just to give you an example of how that particular set looks like, if I take a platform that can do machine learning operations, MLOps, these are some of the major open source platforms. And then particularly, if I just take Kubeflow, maybe you have heard of this particular orchestration platform called Kubernetes. Kubernetes is a very popular open source cloud orchestration platform that help you orchestrate your virtual machines, your containers, Docker containers. And Kubeflow is a MLOps platform based on Kubernetes that also says it is open source, absolutely free, and it is ready to be deployed along with your Kubernetes cluster. And it has a bunch of components that will help you serve your unique ML ops needs on how you want to leverage. So if I just take an example of the experimental phase with Kubeflow, about your choosing the algorithm to experimenting with a given data and so on, each of them you have a bunch of components that are provided by Kubeflow, and you can pick and match. You can take what is needed based on your requirement. And the same goes with the production phase. When the product is deployed, again, since it is Kubernetes based, Kubernetes is available all over. You have Kubernetes services available from AWS, GCP, Azure, everyone, all the cloud, or you can have it in-house, your own server. So you can make use of these things to, for example, train the model or monitoring the model's performance, get your feedback, everything automated. And finally, so you see this for an example, one example, for example, if you just want to use for an MNIST data set, the stack at different levels of your machine learning phases looks like this. Like, for example, you may choose a TensorFlow CNN model for the algorithm and Jupyter Notebook for, so as you see, all the blue colors come from your Kubeflow, and it is nicely automated set. And the beauty is everything comes from a UI. So even a non-CS person who is not well versed with all these technologies, once set up with a Kubernetes cluster and a Kubeflow setup, they can start working on it almost seamlessly, very easily. So that's the advantage, or that is a perspective. And then What do you need to kickstart your MLOps journey? So essentially, this is my takeaway, the takeaway for this session. As you can see here, you should be agile. You should have your system adaptable or able to change immediately whenever an issue is detected, whenever you want a new things to be something new to be added. So things like that. And automation is extremely important. Like at Salesforce, we used to have a team only for performance testing. So they just do a stress test all over the time to the product. And so forget about all other types of testing. And that is a way, and it is absolutely automated. The entire continuous integration, the entire system is automated. So the moment you write a piece of code and check in, the test cases get triggered and it goes through the whole process. And deployment is very important, which should be taken care. I mean, continuous integration should be taken care over there. And scalability, availability, and reliability, all these utilities are very important. And as I said, the observability considerations are equally important. There are a lot of companies who give ready-made observability solutions, things like monitoring and alerting. And do believe me, visualization is equally important. I mean, you get an alert, you get a problem. How do you get it visualized? How quickly you can get into the trouble and go and fix it, find the root cause. So visualization is also equally important. Then the tools, as I said, there are a lot of cloud-based services available, whereas many of them are open source. Kubernetes is again a good example. It's absolutely open source and free, and then it is enterprise ready. I mean, except probably the support part, the entire Kubernetes setup is industry ready. So that means you can easily use it within your own system. You don't need to pay anything to get it up and running. And then the orchestration approach, whether do you want to use MLflow or something else for the orchestration, and then the entire monitoring path. Okay. So with that, let me thank you.
Thank you very much, Dr. Ganesh. We don't seem to have any questions
Okay.
in Padlet. I'm still looking at the audience here. Are they typing?
Yeah, maybe any comments or feedback?
If not, thank you very much
Thank
to
you.
our multi-talented Dr. Ganesh. Next, we have Assistant Professor Clayton Miller from the Department of the Built Environment, College of Design and Engineering. He will be sharing a very endearing topic to us educators in CS. Lessons learned in teaching coding to non-CS NUS students and the development of MOOCs that reach thousands. Yes.
Great.
Prof.
Thank
Clayton.
you. Thank you so much. Thank you to the planners for the invitation. I'm with my presentation. I'm going to try to switch gears. The last two speakers dove into a lot of the really good details behind how models work and how we can deploy them. I'm going to be talking about the really practical side of trying to teach data science, coding, machine learning, whatever buzzword you want to use, how to teach that to students that aren't sort of expecting to be taught coding in a sense. And so lessons learned, like how can we help steer this big ship of data science and computer science towards different contexts, different areas of application, essentially. So a little bit about my department. I'm from the Department of the Built Environment. We are sort of the technical arm of the sort of architecture duo, Department of Architecture, Department of Built Environment. And we focus on the development of technologies to enhance the indoor environment. So aircon, lighting, the different ways to improve the performance of buildings, the comfort and satisfaction of people in buildings. In my group specifically, we focus on the data science aspect of that. And so we have engineers, we have architects on the team, computer scientists, and really looking at ways to leverage sensor technologies, wearables. We're messing around a little bit with computer vision and various things to apply to the built environment to improve the way buildings operate and improve people's comfort. So if you're not, so I want to bring the aspect of context into the machine learning discussion. This was brought up a few times this morning. How do we get these really interesting problems that impact certain industries into the discussion of teaching machine learning or data science? So if you're not familiar with the construction industry, this is an article from The Economist, which really exemplifies the problems we have in the building and construction industry. Efficiency is not happening at the same rate or even at all as compared to manufacturing, retail, and other industries. So this kind of graphic kind of shows it all. Like you've got, of course, agriculture, manufacturing, retail really being transformed. And the construction industry actually work efficiency peaking in the 1970s and actually going down ever since. So what's going on? Why is technology not also giving us these efficiencies? Why is digitization and these things not helping us as much as other industries? And the answer really is, like this architect says, we're still in the Walkman phase. I give this slide to my students and they have no idea what a Walkman is, obviously. I think a lot of the people in the room might remember that. But we're just using technology, but we're thinking about technology in the wrong way. We're using it actually to give ourselves more work in the construction industry. We're making it easier for our clients to make decisions and change their minds and things. It's actually giving us more work in a sense. Every building is a snowflake. It's a prototype. We don't get the economies of scale that the manufacturing industry gets. And so we have a lot of challenges that are very specific to our industry. And this is a slide that kind of shows the different entities of the last 15 years that I've been talking to from industry and academia. These are all entities that deal with data from buildings. So either, and you see a lot of university logos up there, talking to facilities management departments of these universities, talking to researchers. You see a few Singaporean companies, a few US and European-based companies. All of these organizations really say that data is being created on a massive level in the built environment, in the design phase, design, construction, and operations phases, but no one's really using that data, okay? Why are they not using it? I'll get to that in the next slide, but there's, you might not have heard of these data sources if you're not from the industry. You've got building information models, three-dimensional models of buildings. You've got construction management, scheduling, budgeting systems, energy management or IoT systems deployed in buildings, and you're collecting data from occupants through different methods. And there's a huge lack of understanding of how to even use these data for business models and for making an impact in the first place. The other big feedback is not necessarily that they're telling me exactly that we want people with coding skills. They're telling me when I interview these people, we need people that are data literate, and it's very hard to convince data scientists to come work in our industry, okay? So, professionals in there's lots of really smart people in the built environment, but most of them, spreadsheets are, Excel spreadsheets are the #1 tool that's used. Data scientists are very hard to recruit. And so there's this need like, hey, can you guys teach people coming into industry basic data literacy, data science, not super fancy stuff yet, but just basic things. And so this is the slide that I show my students. I basically have 2 full lectures where I convince them first off that learning how to code is a good skill for them. I say that, it's going to help you automate workflows. It's going to help you work with large data sets that don't fit in Excel. And most of all, it's going to give you a glimpse into that language that we use to communicate with robots and AI and all these buzzwords, kind of demystifying the language in that sense. So since I joined NUS in 2017, I've developed 3 courses in collaboration, the first 2 in collaboration with other professors, but the third one just on my own. An entry-level first-year course called Digital Construction. Once again, not scaring the students, kind of something generic that's really helping them grasp the digitization of our industry. And in that course, we teach basic Python, which I'll talk about in a second. AI applications for the built environment. This is for the students that kind of like, we sparked something in their interest and they want to take it further. They actually want to dive into the modeling process. They want to learn deeper skills. And then the last course is a graduate course for our master's program. And these are usually working professionals that are working part-time from industry and coming and taking our courses. So the key here really with these courses is not just teaching the basic Python and pandas, it's also giving the context very, very clearly as part of the assignment. So it's a data set from the built environment that they care about. It's not a generic puppies versus kittens kind of machine learning, type of problem. And this resonates, especially in the graduate level, where people want to see how they want to learn how to code, but they want to learn something that helps them very quickly in their job. So yeah, it's teaching Python to these students. Since 2018-ish, we've had about 600 or so students go through this first year course. The BPS program, the master's program, 80 plus students. Here you see kind of a few photos that I posted on Twitter of our students. And really, and I'll talk about in a second, the key behind this and the lessons learned. The first year I taught this class, it was a bit painful. The second year got a bit better. I'm sure you guys all who are educators understand that process. But I want to help, if you're thinking about doing this kind of thing, I want to help you avoid some of the mistakes that I made. The first one that I found is really important is to not have the expectation that the students are School of Computing students, right? They did not come into university expecting to code, and I don't expect flawless code, basically. They're not being asked to produce code on their exams. I'm not looking through their code and finding inefficiencies or that kind of feedback. I'm really exposing them to code, and I use a platform, I think was mentioned in the last presentation about Jupyter notebooks. These are really, really useful interface for teaching people how to code or anything. And I use Jupyter notebooks, but in the context of what's called the Kaggle platform, which you all might remember or heard about in the context of machine learning competitions, as was mentioned this morning before lunch, machine learning competitions. Kaggle hosts dozens of these competitions, but they've also developed a lot of really awesome tools to learn how to code and machine learning techniques. My team has posted dozens of data sets on Kaggle that are specific to our industry, but there's also like 600,000 notebooks on Kaggle and 25,000 data sets that they can also see examples of how to do various things and learn by seeing how it's done and replicating that. Another thing that's extremely important that I learned the last few years is that group projects become extremely important in the context of teaching coding to non-CS students. There's a much wider diversity. I've never taught in School of Computing, I'm just assuming. But in our program, there's a much wider diversity of speed at which students will grasp the concept of coding. If you have a group of 5 or 6 students, 1 or 2 students, there's a spark that's kind of initiated. They get it. They kind of, they enjoy it even. They won't admit it to their friends, but they kind of think it's cool. Then you've got, a few students that are like, this is okay. And then you got a few students that are like, no, this is terrible. I hate this. This is a new way of doing things, and I'm really struggling. So getting students into groups and explaining to them that the concept of teams, and here you see, this is from a book called Doing Data Science, where they say, there are 7 different, I can't get the laser to work, but there's 7 different skills that really pertain to data science. And you can see them there on the left-hand side. The point of a group project is to not have everybody maximize skill in all 7 areas. The goal is to figure out the strengths and weaknesses of the individual members so that the combined team can be somewhat well-rounded. And if the team, and of course, a lot of my students don't have the hardcore statistics and mathematics backgrounds. So that's a part of that they know they're missing. They know they're not doing super advanced modeling techniques, right? But they're figuring out what their strengths are on the team, and they're leveraging that. And the end goal of their project is not necessarily code. It is a presentation or a report that they need to create in the context of a decision maker. And I tell them, no boss is ever probably going to care how nice your code is, unless you work for like a tech company, you really get into that. But a lot of times your boss may be non-technical. They want to know what we can learn from the data and what decisions we can make from that. So the communication side, the visualization side, the context or domain experience side is more important even than the code in these group projects, at least for the first year students for sure. As we get into the more advanced levels in the graduate level, then I do expect them to grasp more and more of the technical side and the coding side. So I showed that slide a bit ago with all those companies that I've been talking to after years and years and years. And I see that there's a huge untapped demand. And this is something that I've been very passionate about even before I did a PhD. I was in industry for a few years. And I wanted to reach out to all these architects and engineers and construction managers and really open their eyes of using basic data science besides using a spreadsheet, using Python instead, and what it can do from them. So people would always ask, well, how do I get started? And I'd say, well, there's a lot of online courses where you can learn Python. Python is the key. It's the easiest language to learn and these type of things. But it wouldn't really resonate with people when they started these programs. They're very generic. It's very focused on really fundamental ideas. And working professionals, they lose interest very quickly. So what my goal was about 3 years ago to start working on a context-specific data science online course, which we deployed a few years ago. We deployed it in April of 2020, which was the perfect time ever to deploy an online. Weirdly, the timing worked out amazingly. Everybody around the entire world was sort of staying at home and looking for something to do. So we launched this in April of 2020. And it's been a really interesting experience to try to scale this into what's called a massive open online course. So I'm going to tell you a little bit about that path as well. Getting started. So if you didn't know already, there's actually a lot of support for developing online courses. In fact, there's a big push to digitize parts of courses to create flipped classrooms for your usual classes, which I have been doing even before the edX course. And I thought, well, let me adapt some of this content I'm creating for flipped classrooms, enhance it, make it better, make it a little more polished, and just deploy it to the industry as an online course. So these are some tips. You know, please teach your course for a few years before you try to do something like this. You need to care about the larger community. It has to be a passion. You won't survive just based on ticking the box of doing a MOOC. You have to really care that you're reaching out to a community that you are very familiar with. You need a creation strategy, what types of content you want to create, how much time you want to spend on different types of content. And then the CIT, CDTL teams and LIFT funding. So Professor Earl Lim and his team are really, really supportive. You reach out to them, they help you find the resources you need. And edX training seminars were helpful as well getting started. Let me talk a bit about my course. At a high level, there are 3 types of content I create, and these are also synonymous to what you may create if you want to create content for flipped classrooms. 20% of my course is studio TV style, where I'm standing in front of a camera and, there's a teleprompter and it's really that kind of polish. That's about 20% of the time. It takes a lot of work. You have to read the teleprompter perfectly, or you have to start over, stuff like that. Then 30% of it is recording booth with video, with my face. So I'm in the recording booth by myself. I'm sort of going through slides or concepts, and you can see my face down here, and I'm kind of talking to the students. And the remaining part of the course, because it's a coding course, is just screencast. There's just my voice and there's the screen. And I post-edit it, and I have CIT helps me to zoom in on concepts and add fly-ins and all these different cool things. But it's really just screencast with voice. And the decreasing level of effort in that sense goes from top to bottom. If you want your edX course to be all video style with TV style, it'll take a really long time. It'll have a high budget. If you want to do other types of content like I did, it can be done in a little bit easier of a way. So it's up to the person. It's very much, if you look at edX, NUS edX courses, there's kind of a broad range of how this works. There's no right or wrong way. You do want the content to be quality, of course, but there's different ways to do that and different ways to 80-20 it, in a sense. I did get LIFT support. I did put a lot of hours into it. I piloted the course, so I sent it out to various people from my industry before I launched it to a large mass of people and said, hey, take this course, give me feedback. I got lots and lots of feedback from industry. Creating evaluation metrics. So of course, it's not a final exam like NUS. It's much more simplified evaluation, but there is a path on edX called a verified certificate, where people are actually paying a relatively small fee as compared to a university degree to get a certificate. So you have to come up with ways to provide that evaluation method. So launching, I've been blown away at how many people. At first was very overwhelming, a bit scary, but over time I got kind of used to it. I've launched it 4 separate times. The first 2 times were what's called instructor led, where I actually every week would release another section of the content, and I would really kind of handhold the participants through each of those sections. But the last 2 releases have been learner led, so that the actual I release all the content, and the student just goes through it at whatever pace they want to go through it at. It's a little bit something you do after your course has been kind of has a bit of a track record behind it. The instructor led is, of course, it takes you're really paying attention to things a lot more closely, and you're able to make modifications in a new course in that sense. So 24,000 people enrolled over the last since April of 2020, almost 2 years. 1,100 of those being paid verified track users, which is really awesome yet scary, but it's also, you get used to it and you learn from it, and it's been a great, interesting process. A lot of the people that take the course, this is from edX, they have an insights page. You get a sense of who's taking the course throughout the world. Mostly people with at least bachelor's degrees, over 80% with bachelor's or graduate advanced degrees, from all over the world, the biggest being the United States, and then India, and then Singapore, but over 110 countries total represented across the world. So a lot of breadth and reach. That's really what edX provides, is they have a platform, but they also have a lot of users. And in fact, April of 2020, they said was the highest peak number of users they've ever had, right? So it's really edX, that's the value they provide, is the online environment, which helps bring people in. I was really blown away to be nominated for an edX prize in innovation, and was one of the finalists last year. I was rightfully not, I won in a sense because my competitors were a course about volcanoes, which was really cool. They had fly-ins of volcanoes. There was a course about making beer, which was also pretty cool. So I felt like the competition was pretty stiff. I didn't actually win, but I was really happy to be a finalist, which was great. And the innovations, this is a prize for innovation. So the innovation that I was working on was reaching non-traditional sort of coding students. So students that are from a certain industry, and adapting machine learning curriculum to that. The best parts for me is the feedback, the comments. So people reach out on LinkedIn, send emails. I have a survey that I give. Lots of great feedback, which makes me feel like I'm making an impact. That's really been by far the best part for me, is to understand how it impacts people. And also, taking that advice and feedback and understanding how to improve the course, which is what I'm in the process of doing now. So that's another heads up, that if you create courses like this, you do, especially in machine learning, have to update them very quickly, because of course we all know it's a very moving target when it comes to teaching machine learning. Last thing, with any questions, also a couple recommendations, 2 books that I use to structure my courses, teaching data science and machine learning. The one on the left is where I got a lot of the stuff where I teach the students about how to build data science teams. The one on the right is by far the best book I've ever found to explain AI to people, to non-technical people. Really breaks it down in very simple ways, very pragmatic, profit-driven ways, if you want to call it that. But it's great. I suggest this to my students that are taking the level 300 as well as the master's level, to really get a sense of, great, how do we actually end up applying this in a real company? So with that, I'll answer any questions that you all might have.
Thank you very much, Prof. Miller. So while we wait for questions to be populated at Padlet, so far we don't have any yet. Probably let me start.
Yeah.
Yeah. There's a part of your speech or your talk that strikes me. You mentioned that projects are important. Yeah. So you have to have a good mix of members so that they have the correct type of attributes.
Right.
How do you get that started? Because we do have this kind of situation in CS where birds of a feather flock together.
Right,
So
right.
good programmers, they just bunch up together. Yeah. So how do you find that good mix?
That's a great question. It took multiple years to figure out the right formula for my course. In the beginning, I let the students pick their own groups. They like that. I stopped doing that. I said, I pick your groups. They complain, but I say, look, I'm training you for the real world. You go get a real job. You can kind of pick who your colleagues are based on, weighing your options of what job you take. But once you're in that company, you don't usually pick your teammates. So first year students, I randomly, the algorithm, there's a Luminous picks for me, the different breakdowns. The objective of the first year course is such that it's not too bad if you have a bit of imbalance. Graduate level, I have a survey. So I ask the students to fill out a sort of a demographic skills-based survey, ask them if they have coding experience, what their background, job, all these things. And then I hand design the groups, and I also explain in the same way. And I find that if the students, if they understand my reasoning, they still grumble a bit, but they don't revolt in a sense. That it's not like they kind of get it when I really emphasize why I'm trying to do it. So, but yeah, that is a key factor. Yep.
Okay. Thank you very much.
Yeah.
Any other questions? I'm still having no posts.
Mm-hmm. 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 Mm. Yeah, those are great questions. I'll grab the second question first. That is definitely something I pay attention to. So in our graduate programs, we have a lot of students from overseas. So I try very hard to ensure that you have a good mix of people from different backgrounds, cultures, like gender balance in the groups, things like that as much as possible. Because I find that because the end goal of these group projects is a presentation or a communication-based document. And the more diverse the group, the better that end documentation is, because the students can't just communicate in the same old way. They have to think of new ways to communicate with people that are not like them. And so it's amazing to see the diversity factor, I think, influences that a huge amount. Your first question about how to create groups on MOOCs, you can't. As my first few launches, I wasn't able to do that. I'm renovating the MOOC now. One of the things I'm integrating is peer feedback. So you won't be part of a group, but you will submit a Kaggle notebook. That notebook has code, it has explanations, it has graphics, and you have other people in the MOOC that are looking at that notebook and giving quantitative and qualitative feedback to help that person improve. Because also the objective is a notebook which conveys a point. I'm trying to figure out exactly, but it's really tough, but you have to start using the more advanced tools on the edX platform to do that. Yeah, great questions. I think I ran out of time though, right? So, okay. Thank you.
Thank you very much, Prof. Miller.
Thank you very much.
Okay, I'd like to thank our 5 speakers today. I think we've had a really good series of talks today. At 2:45, we will start on the panel discussion. Okay, so let me just check whether my panelists are here. Associate Professor Andres, Dr. Dennis Kachenko, great. Wikek, I know is here. Dr. Ram Singhi, great. And Riantek, I know. Okay, great. So we'll take a short, maybe 10-minute break, and then we'll come back about 2:40, right, to begin. So I just wanted to comment about Clayton's talk. I didn't know that you could do an edX on making beer. I used to make my own beer. I should have done something. It's a great call. Okay, so we'll see you all of you in about 10 minutes. Thank you. So I'd like to invite our panel onto the stage. We have Associate Professor Andres Depeler from the Department of Strategy and Policy, NUS Business School. Dr. Dennis Kachenko from the Department of Economics, NUS College of Humanity and Sciences. Associate Professor Tan Wee Kek from the Department of Information Systems and Analytics, NUS School of Computing, Dr. Lam Sing Yi from the Department of Mathematics, NUS College of Humanities and Sciences, and Dr. Lee Yan Teck from the Department of Finance, NUS Business School. We apologize that Professor Greg Tucker cannot join us today. So please can proceed on the stage. We'll have a very, I think we're gonna have a very, very interesting discussion today because we have a really cross-disciplinary panel here. So, you know, we encourage you to grill them and ask them a lot of questions. Thank you.
Okay, good afternoon, everyone. So in this session, we're going to be discussing curriculum design for AI-related modules. Right. So in the session, well, I'd like to thank first all our panelists and to all of you who are here, like on-site and online. Hopefully, we'll have a nice discussion on actually the issues that we have in producing AI-related curricula. Right. So I'd like this session to be broken down into a few parts. So firstly, we'll be looking at key learning objectives within an AI-related module. So at a high level, what are the learning objectives you think that are important? Right? Based on the kinds of students you have, what do you want to teach them? In association with that, we also want to think about the prerequisites that are related to those learning objectives. So what do you expect your students to already know coming into your classroom? Right? How do you ensure these things? Moving on, we'll look at modes of instruction. So mechanisms to actually teach these students. What are some examples? Perhaps our panelists will be sharing. What are some examples that have been successful or not so successful in conveying this content to the students? Following that, we'll look at difficulties. Don't worry, I'll cover this all again later, but the difficulties in different kinds of situations like large classes or differentiated classes. And then finally, I think we'll look at assessments, right? How do we actually assess students? And then we'll take open questions after that. Okay, so I guess we'll begin by having introductions from our panelists. So maybe you could briefly give an introduction in terms of what you teach in terms of AI. Thanks.
Okay, so hello everyone, and thanks for having me here. I'm Denis Tkachenko from Department of Economics. So I teach a couple of classes in the Department of Economics, which are titled Machine Learning and Economic Forecasting at 4000 level and Applied Master Program. I also happen to be one of the co-directors of the new interdisciplinary degree, Data Science and Economics, or DSE for short. And so in that program, I also teach, I co-teach with a statistics colleague, Yuting Huang, the first course entitled Data Science for Economists.
Hi, I'm Yan-Teck Lee, Department of Finance, Business School. I teach the 4000 series, data analytics in finance, and also at different level, MBA students and undergraduates. That's pretty much all.
I'm Andreas Steppler. I teach at NUS Business School. I have two modules. One is called Emerging Tech and Value of Data, the MBA program. The other one is called Big Data and Business Strategy for the master's program, and both of them include AI and other technologies.
Yeah, hello, good afternoon. I'm Xing from Department of Mathematics. I joined the department 2 years ago. I teach 2000 DSA modules, numerical computations. So basically the modules teach students how to use computer to solve mathematical problems. We will teach students the mathematical theories, and we also teach them how to code. And secondly, I teach optimization related courses like linear programming and complex programming. Yeah, that's 3,000 module.
Hello, everybody. I'm Wee Kate from the Department of Information Systems and Analytics, School of Computing. Other than teaching data science modules in the department, I'm also one of the coordinators for the AI competency courses that the president mentioned earlier on in his morning address. So in this competency program, we are actually targeting all the E&A staff in the university to teach them AI. And as you can imagine, they come from a diverse background without computing knowledge, very similar to the general undergraduate student population that we hope to impart AI to. So I hope to share some of my experiences over here. Thank you.
Okay, thanks for the introductions. Okay, so we'll start with the learning objectives you think are relevant to your modules. And in particular, what prerequisites you have for them. Because I feel that one of the issues that we have is your students might come to you in the module where they say, you know, I've taken a prerequisite module, but it may have been a few years ago, and they may have forgotten the material. Under these kinds of circumstances, what do you normally do? I mean, you might have these prerequisites, but if they are not updated with your students, how do you actually manage that? And maybe I can open this to anyone to answer who has experienced these kinds of issues. No one? No one has encountered this? Oh.
Well, so I also happen to teach econometrics, which is kind of like the statistical side of economics, working with observational data, and it's a sequence of classes. So there's like foundations, econometrics 1, econometrics 2, and they're all like a prerequisite for each other. And then in turn, they become the prerequisite for the machine learning class at the 4,000 level. And so, yeah, you are right. This problem always arises, right? And students, even if they took the class last semester, they complain that, you know, they forgot everything. So I think, well, that's kind of their problem, right? In some sense, I think you can approach this problem from two sides, right? I think on the first side, when you teach the prerequisite class, it's important to emphasize that, you know, what's going to happen in the future, right? So when I teach econometrics 1, I keep referring to, you know, okay, I teach you these guys now, and it's very boring, but they will come this class next semester or next year, econometrics 2, and you're going to apply this in this particular situation, and I try to give them a flavor of what's going to happen. Or if it's a math prerequisite, we also try to give them a sense of a real problem, you know, maybe a very stripped down, simplified version where this math is going to come into play. So that's from the ground up. Right now I'm in the same situation, teaching econometrics 2, and students come and they say, well, I don't remember anything from econometrics 1, or they come from the stats side. So they have done the course for multiple regression in the stats department, but perhaps they missed out on some kind of causal inference emphasis from the econometrics side. And so what I'm trying to do, I was fortunate enough to teach the earlier class a few years ago. So I just provide my webcasts and some kind of a review lecture at the beginning, where I kind of highlight the key points that are going to be sort of very important in the next lecture. So week 2 would be starting the material. And so, and when I taught econometrics 1, right, the foundations of statistics is the prerequisite for that. So I used to spend more time, like 2 weeks, to actually kind of refresh probability and related concepts. But again, more in the context of what's going to come. So I don't know if this is the right answer, but that's what I've been trying to do.
I think it provokes a good follow-up question. How many of you wished you had material you could call upon and deliver to your students? And like, if you don't know this material, please go and revise this now. If you're not, if you haven't revised this material recently, maybe you actually want to look at it. Right? How many of you actually thought you could use this kind of material in your own modules? Yeah, okay.
Yeah, maybe let me just provide my own experience on this question. From my point of view, when we teach AI or machine learning course, right, there are two main prerequisites that the students should know. One is the statistic fundamentals, and the other one, if you are using a programming tool, will be the programming fundamentals. So these are very common domain areas that there are lots of materials out there. So we try to leverage on this existing material to get the students to revise on their own instead of us having to go through the entire motion again. So if I were to share my experience in the AI competency program, right, you'll notice that other than the AI competency program, we have a concurrent program known as the data literacy program that's also going on for our executive and admin staff. So in the AI competency program, we will try to leverage on the basic statistical knowledge that's covered in the data literacy program. So this will negate the need for us to spend too much time to go through all these statistical concepts again. So I can jump straight into the AI domain knowledge. I think this is one good way we can try to leverage on existing resources.
Does that actually happen? So you actually get the students doing the AICC module to actually look at the data module as well?
Right. So that's an interesting question. Some of the participants might have already done the DLP program, so that would be good for them. But some of them might not have already done so. So we can't exactly make the assumptions that all of them has gone through the prerequisite. So for those students who have not, we will still try to have a little bit of primer on statistics inbuilt into our workshop itself, just to make sure we cover the ground. Yeah.
So that's typically at the beginning, you have an introductory session, or is this independent learning that you're talking about?
We have a mixture. So we have a pre-classroom learning where the participants will watch some video and then they will come in for some hands-on with our visual tool. Yeah.
Yeah, go ahead.
Just to share a bit of my own experience. So I have a class for the Master of Science in Finance program, and the students range from lawyers to historians. So you have very wide, backgrounds. So what I had them to do, because they are going to code and they are going to do statistics, so I get them to actually do pre-class learning a month before to pick up their coding, to pick up their statistics through a platform, data camp. And then what I get them to incentivize them to seriously go through the materials, I get them to be tested the first few classes, specifically in statistics, in coding. So the way I sort of motivate them is the following. What you're going to learn is going to be fun. At least I think it is fun. But you have to go through the pain. And this 1 month is where you are going to go through the pain at your own pace, because some of them are, very quantitatively trained. So for those people, they can pick up very quickly. But for those who have no coding statistics experience, they are going to find it very difficult. Now, the question now is, how do you support them? Because for them to pick up something brand new is going to be challenging. So I put them on platforms like Microsoft Teams so that they can ask questions from me, or they can learn from each other. Yes, before the lesson actually starts. So the whole process starts a month before.
So you leverage the data camp syllabus and
Yes.
curriculum. Does it meet your needs exactly?
So I have to basically mix and match a little so that it fits what I hope they would learn before we start the lessons.
Okay, thank you. Anyone else would like to share? Sini, do you have anything?
Yeah, so my module is a 2000 DSA module. Mainly the module is catered for DSA students, data science students, but I actually got some students from Department of Engineering, and I think one student from SDE as well. So I think I don't expect them to memorize all the mathematical theorem they had before. So when I introduce new topics, so I will normally just spend a few minutes to talk about those previous knowledge that they will need. Basically, that's.
Is it usually sufficient?
Yes.
Andreas, do you have anything to add?
I think my situation is perhaps a bit different because I don't teach the students to code. I just try to convey a business understanding of AI and its applications. And so for that, I really start at zero. I have no prerequisites whatsoever.
That's nice.
So just like what Prof. Clinton has mentioned before, I think it is essential to have a team that is diverse. So this is where I spend quite a bit of time to arrange in such a way that each team would have at least one person who is quantitatively trained or who knows how to code. So it's not about a person having all the skills necessary, but having a team that has one of the few necessary skill sets.
So even if they don't have the prerequisites or the totality of the prerequisites, you sort of augment that with the team that they put in.
Team dynamics, yeah.
Okay, sounds good. Perhaps we can move on and we can share about instructional mechanisms that are used within your modules. So perhaps we can have some examples of what has worked and what hasn't worked within your module. Anyone want to start?
We go right or left. Okay, so I think one challenge teaching, non kind of computer science students, data science or machine learning, is that there is kind of a dual skills, right? First is the theory and what is the reasoning behind these algorithms, and maybe some proofs about why the mean squared error is always higher out of sample than in sample, etc. On the other hand, there's the implementation, right? For domain experts, implementation is very important, right? So it's a little bit maybe unlike the math side, right, where proofs are important and implementation not so much. For like econ or built environment or health, right, implementation is paramount. So in some sense, we're trying to teach students enough theory not to do kind of silly things, right, as I like to put it, but we want them to be pretty comfortable in applications. And that actually generates a lot of demand on kind of time that you need to spend on instruction. And so one strategy that I kind of figure out, both kind of teaching econometrics and machine learning later, is that I tend to emphasize, the theory, the motivation, and going through the application and really stressing kind of, interpretation of the output in class, right? So we get 3-hour seminar, which is really 2.5 hours with breaks. And then the coding part, right? I kind of do it. So first of all, I replicate everything I do in lecture. So when they go through the application, I provide extremely well-documented code for that. And then I also do screencast videos. So something that Clayton outlined before, the 50% of the MOOC. I do that and I put it online. And I don't have any requirement for students to watch them. But as been mentioned, everybody learns at their own pace. Somebody can just read the script and say, okay, yeah, I got it. You do this, package this option, I'm good. Some people want to spend more time and listen to the explanation. And but I think it's important not to kind of spend a lot of lecture time on coding, like teaching coding, because everybody kind of gets it at a different pace. And so you end up with a classroom where 20% is bored, 30% didn't actually get to the point you're at, and the rest is kind of following you. And so there is this kind of disconnect that you have. And you're then under pressure to cover less theory. So that's something that seems to have been working so far in my class.
So can I summarize that? So you're saying that you stress the theory before, and then you have them work offline on the coding aspect, so that you don't have to follow during the lesson itself. Like you don't have to walk them through it. Is that what you're saying?
So the lesson is usually structured like there is a motivation, then there's theory, then there's the application, where I show results and I tell them which algorithms I used, and I explain, what the numbers mean and why I got the result I got, and what could be like policy implications of these numbers. And then I leave it to them to work out the kind of the behind the scenes of how I got those numbers, right? Because these days, at least for domain experts, it's more important to, understand, why we're doing what we're doing and how to interpret the outputs rather than actually generating the output.
So you treat the application as more of a black box. I mean, for them, it can be seen as a kind of a black box.
Not really, but because they know what's happening, right? But the exact nitty gritty, right? They go back to the script.
So implementational is cut out.
Like the
Yeah.
dirty details of implementation is cut out.
What he says resonates with me. So what I do is similar. For example, on efficient market hypothesis. So I will pick like Low and McKinney's paper, and then I will replicate the paper. But it's going to start off with motivation, and how do you construct that test? But my emphasis is not on how do you come up with the test statistics, but the actionable insights. Now that you have this number, this variance ratio, and this t statistics, what are the actionable insights? What can you productize out of these particular tests? And in terms of implementation, I agree with you. Teaching students synchronously about coding is a waste of time because many of them will fall asleep. So I did exactly the same. I do webcasting, the code, the data, and the Jupyter Notebook in Kaggle, they're all out there. Do it when you're free. And however, there's one challenge. The challenge is that you really do not know who actually go through that and how much they learn. And what I think is the best is really, so this is what I call the asynchronous code learning. What I find very effective is the synchronous session. So you do not ask them to learn how to code. You get them to code in class with a specific objective, something that builds upon the asynchronous material. And I find this very effective, especially in team setting.
Okay, thank you.
So going back to the topic of methodology, I think one thing that I've employed, not so much for coding, of course, because I don't teach coding, but just to understand what can AI do, is I let students in groups look at the AI as a service offerings on Google Cloud and on Microsoft Cloud. Both of them are very well documented. Both of them have a lot of offerings. Both of them are updated continuously. So I think for me, these commercial platforms that you can actually play around a bit are a good way to demonstrate or sort of build a bridge between theory and applications and give students, especially business school students, an idea, how is AI actually applied in a real business context? How is it priced? How is it delivered to actual corporations? Because I think there's often this illusion that you need data scientists. You need a team of data scientists, and you need to spend a lot of time to actually build a model and train it and deploy it and so forth. But I think there's this second, of course, paradigm now that's becoming more and more common, which is AI delivered through the cloud as a service. And I think that's, for these considerations, I think Google Cloud and Microsoft Azure offer great examples. And then what hasn't worked now, I find it extremely challenging to explain to non-computer science students what is a deep neural network. And I would love there to be some kind of a simulator that you can give to lay people and let them play around and sort of develop an intuitive understanding. What's an input layer? What's the output layer? What happens in between? What kind of concepts are formed? Vital model as data sort of flows through the nodes. And that's something, I mean, I usually try to explain it theoretically, but that usually gets fairly obscure and esoteric at some point. So if there's some kind of, as I said, simulator or something that allows students in a little group exercise to play around with it, switch some parameter, see what happens, I think I would consider that a really useful pedagogical tool at a non-technical level.
Does this apply to other models, or is it just the deep learning neural networks that you need this for?
So yeah, just to answer this, so at the very basic level, right? There's this website called TensorFlow Playground. Have you heard of it? Yeah. So it gives you like a very simple network, and you at least can kind of get the idea what changes when you change basic components.
I've seen that. I've tried to use it. I found it a bit too challenging for my students, but maybe it's just a way, maybe it needs to be very well prepared. But this TensorFlow simulator is actually quite good. Yes.
Yeah, so actually I agree with you guys when you talk about the implementation of the algorithms. So in the lecture, right, we do not really have time to go through the implementation in details. So normally I would just go through pseudocode. So I would just point out important things that the students should take note of to implement the code. And yeah, I will put the actual code and the Jupyter notebook in Luminous so they can download and study them whenever they have time. And yeah, and also in lectures, we do not have time to really let the students try to solve some practical applications. So yeah, normally I just come up with some simple examples or simplified version in the lecture so they can solve. And in the homeworks, then I will ask them to solve some real life application. So they might need to like download the data sets themselves and apply the algorithm that we have learned to solve the problems. Yeah, so it's a good thing.
Maybe I'll just add on to this discussion with sharing one of my own technique that I use. When we teach AI and data science, one of the tools that we use is a no-code visual tool, such as RapidMiner Studio, Orange, or Azure's ML Studio. So sometimes when we find that it's difficult for students to follow through the code, we use such a tool to repeat the entire machine learning workflow first. So students have a very high-level mental picture of what they need to do. So from there, we can ask them to go back and study how to implement it with a Python code or R code, for example. So this sort of gives them some scaffolding, and from there they can compare their answers with what the visual tool come up with. Yeah, so I find that helpful in my own teaching too.
I think so far, most of the things we've discussed are about a student learning your material sort of independent to other students. But what about in the setting of peer learning or learning within groups? What have you done within your modules to actually facilitate this?
Well, in my case, I usually ask them to write a paper in groups, an essay, an academic essay, 2,000 words, but not just about AI. Actually, I just give them a certain topic selection about technology, recent technologies embedded in a economic, business, societal context. So that's how they work together. That's how they do research. That's how they write it all up. There's clear expectations, and but of course AI plays, if at all, it only plays a very small part, either as sort of as an enabler, as an underlying technology, or perhaps in a more sort of material context. Because I usually try to not just teach AI as something immaterial and kind of in the clouds, but really also talk about sort of the material underpinnings, the infrastructure, the data centers, the electricity consumption, all of these aspects, which I think are important to understand AI as in an economic context, which probably are often glossed over or just not covered at all in a sort of typical computer science module. Or maybe I'm wrong.
So I did two things. In one module, statistics and analytics in finance, I give them a project, and this project would end with a presentation to a fund manager, and it may potentially end with an internship. So back then, the background story is COVID-19, and how do you position your portfolio? And they are supposed to come up with creative ways to apply whatever they have learned, including application of machine learning. So that's one side. They really work hard to find new sources of data sets and new way to interpret and coming up with new actionable insights. The second one is some kind of peer review. So team A review team B's work and give comment. So they have initial submission of their Jupyter notebook, and then it will be reviewed. They will be given chance to resubmit, revise and resubmit in the second round. So this is, I think, where they learn a lot from each other, from code efficiency to whether the test is correct, to whether there are better data sets or API that you can tap into.
So similarly, I use a group project as a kind of a consolidating tool for all that's happening in the class. So the structure is usually I leave it up to the students to pick their topic and the methodology they're using, and even the language they program in. But I do provide them a lot of guidance on where to look for data. I provide, because in economics, right, it's kind of the lines are blurry between econ, finance, and some other fields, right? So I provide them a selection of papers on prediction in the literatures for example, exchange rates, financial things like stock return prediction, and more traditional like macroeconomic aggregates like inflation, GDP growth, because all of this data behave differently, and so different methods will be successful or unsuccessful depending on that. So I give them a bit of a taste, what it's like to work on each particular data set. And so from that, they form a proposal around mid-semester, which I then review and give them feedback, mainly to make sure that, the topic they chose is feasible within the, time frame, and also whether their data would actually support the analysis, right? Because as you know, you need to have a training data, the testing data, and if your testing set is too small, then your results are basically meaningless, right? And I also update them on the methods from the current literature that they could implement, which are not necessarily covered in class, right? I actually encourage them to go and build up a little bit above the basic methods that are covered in class. And at the end, they do a presentation and a kind of a short technical report / research paper write-up. I'm still kind of playing with the idea. I think this semester I'm implementing also the peer feedback, which will come at the end. So I would ask them to record the presentations, and then each group will provide feedback on 2 out of, say, 15 presentations outside their area of expertise. So, if 2 groups are working on inflation, I prohibit them to peer review each other because they are too familiar with the topic, right? So they should be able to comment more generally on applications of machine learning from not necessarily the field they have already extensively researched. Yeah, and I also had the group homeworks, but one constraint they hit is that there is actually like a limit on the weight of CA you can assign group work to. So I actually now weigh all of it on the project, 30%, and then yeah. But I do think in the background, they collaborate on homeworks, and so there is sort of shadow peer learning happening still.
Okay, I also utilize project-based learning heavily in my own teaching. But one distinct thing that I actually use is that I will divide the project into 2 distinct separate phases. So in the first phases, students are asked to put out a project proposal or project plan first, where they must clearly articulate the business objective of applying machine learning or AI. And then they will talk about data requirement, the algorithm that they need. So the other benefit over here is that through this discussion, the team members can get to know each other if they are from different background. And at the end of this project planning process, we actually get groups to do a presentation among their peers so that they can get feedback from their peers on how to better improve their project. So for example, the peers might provide feedback on where to get the correct data. They might provide suggestions on what better algorithm that they can use. So through this process, they will have a much more refined plan before they actually move on to the implementation phase. And it can also involve the whole class in the project discussion process.
Yeah, so for me, I will ask students to do tutorial presentation. Yeah, so in every tutorial session, student is going to pick 1 or 2 questions to present. So they will need to explain their steps clearly in solving the problems. And they are also expected to answer questions from their peers, from their classmates if there's any. So yeah, rather from learning from me only, the student also learn from their peers.
Are they in groups when they do this?
They were assigned to different tutorial groups.
No,
Yeah.
I mean when they present, are they presenting as a group?
Oh no, they will do it individually. Yeah.
Okay. It sounds like the experiential learning via projects is a thing that's pervasive across all of the modules. But what about small scale projects versus large scale projects? So maybe we can pivot over to assessments. It sounds like most of your projects are more large scale projects where it's the one off. You do the one project, you get your mark for this one project, you're done. What about the micro projects or the smaller projects leading up to it? Do you actually scaffold the project in any way, or do you actually think breaking up the project might actually help?
So I also give them homeworks. Usually maybe 2 or 3 assignments per semester, which are quite substantial. And so what's happening in those assignments is exactly as you said, it's like a micro project. So I give them data, which is maybe smaller scale than what they use in the project. And I give them explicit instructions, what they should do with that data, right? And so through that, they kind of get the understanding of the process, how do you go about? So first you plot the data, you notice any irregularities, do something about them. And then you go on to your, benchmark model, your competing algorithm, et cetera, then you look at the performance. And so they do it with a variety of techniques, right? So throughout the semester, as they're learning new methods, and this also allows me to kind of give them, a sort of the skeleton code, right, that they can then recycle in their project with a bit more understanding and augment on that. And so I think this provides kind of scaffolding. And again, I noticed that, even though this is the individual assignment, they do actually discuss a lot within the project groups. So I can see some similarity, in reasoning and code. And I don't discourage it because, I think that's really where peer learning is happening.
So I have similar setup as well. I call it problem sets, so Simon's problem sets. And they are basically foundation for them to deliver the project. So I have one midterm and then one end of the term project. Each of them would be, the finale for the earlier sessions. For example, week 1, I talk about Monte Carlo, week 2, they are supposed to mix and match different algorithm to productize something that is useful for a persona. So this, I think, is one area I challenge them to really think about how they turn whatever idea they have learned into products, into something that is actionable for someone and valuable for someone.
And before we move on, can I just check? In these problem sets, in the micro assignments, do you actually link it directly to explicitly link it to the final project in any way?
No, because they all are doing different topic, right? But what's helpful for them is that they see a real life application of a particular algorithm, right, to a particular data set. And so even though it's not exactly what they're doing in the project, they can leverage on a lot of even the code structure, right? How you input the options to a particular package and how you iterate, for example, in time series, right? You have this iterative prediction of observations over time while moving the training window. And so they get all this stuff that's kind of essential tools for building up the project, and then they just incorporate them into whatever they're doing. So it's not helpful equally for everyone, right? Everyone's project, but I think everyone can find something in those assignments that would leverage, their project work.
I don't restrict them as well, and sometimes I get blown away by what they deliver because of the no restriction, because they come up with things that I don't teach them, and something that I don't expect them to deliver. So, for example, some of them come up with technical trading strategy and then how to put them in the portfolio with the optimal way and then deploy to the server. And some of them marry analytics that I didn't teach as well. All of these are, an attempt to push them to their limit to come up with something that is valuable for someone.
I mean, I just have one big project, but one thing that I've tried is to ask them to give a midterm or interim presentation after or in week 6. And so that's for me also a good way to see, are they on track? Do they have a clear sort of structure? Do they know, have they already done enough research? Because what I of course want to avoid is that everything is done in the last minute. So that's so the final deliverable is of course a report written, an essay, but the interim deliverable is a PowerPoint presentation held in class.
What about
Yeah, actually, I did not have experience on giving students big project yet, but yeah, I always want to design one, so it's good to learn from the other panelists here.
Okay, I mainly work on a single big project that the student do throughout the semester. But since we are on the topic of assessment, right, maybe I could share my own experience with a practical exam. So it's actually some kind of a small mini project, just that the student have to do it within the time constraint that we give to them. And this is a very typical technique that the computing folks do for our programming modules. So I basically extend the idea to data science and machine learning. And we structured the entire practical exam in a task-based format, where each practical exam task is mapped to one of the intended learning outcome of the module, or for the matter, one steps in the machine learning workflow. So for example, we ask students to perform data ingestion, data cleaning, then followed by feature engineering, and then machine learning. So we structure this task in this way. So at the end of the whole practical exam, they will have gone through the whole cycle. It's some kind of a mini project, but we can have a very good gauge of whether the student can independently complete those tasks by themselves. So that's what I do in my module.
So since it's more structured, the module you're talking about is more structured, the content is very specific. Is that what the reason, the rationale behind why you have a practical exam, so that you can enforce, you can require the students to actually know how to perform certain things within the entire ML process?
It needed be very structured. So for example, I've done this for a text analytics course before, and also done it for a typical machine learning course that uses structured data sets. So it's not exactly very structured, but the idea here is that you need to perform certain key tasks in the machine learning pipeline, and we try to test whether they can actually do this task through the practical exam itself.
Okay, perhaps we could move on. Wait, does anyone else have anything to share in terms of assessment? Anything interesting that you've used as an assessment?
I think in terms of assessment, there's a difference between, different type of audience. Some audience, they want to scale the mountain, but some just want to get up to the mountain to ski. So I think for business students, they tend to be the skiers. So the question now is, how do you design assessments that test them on actionable insights, implications? So my exam, especially for the MBA students, tends to be very light on coding. For example, I asked them to write pseudocode instead. But for the undergrad students, because some of them are from CS, so I would get them to do harder core, kind of coding. So my point here is it's really a function of your audience. For MBA students, if you ask them to code, I think you'll be fired soon.
Okay, so perhaps we can move on from anyone else have anything to add for assessment? No? Okay, so maybe we can move on to one last segment, and then I'll look at some of these questions. But in terms of what you feel you wish you had, so moving like in terms of the modules you designed and implemented and conducted, what do you wish you could have? Like maybe if you could ask SOC perhaps to lend you some material or content, what would it be? Or anyone basically?
Well, I think what would be really helpful is a domain relevant textbook, right? So something like machine learning for economists, right? It just doesn't exist at this point. So this is, I think, a challenge for any kind of domain related course, because if you look at the standard textbooks, like, Elements of Machine Learning or Introduction to Machine Learning, they are great books on statistical learning, right? But it's very hard to motivate students, as Clayton has said, that, you're looking at these problems, which could be, cancer cells, but we're doing economics, or pictures, but we're doing economics, and students are like, well, how is this all relevant to me? Also, some machine learning books, they focus on stuff that's more useful in a kind of what I probably, selfishly call like more machine learning, kind of deep learning oriented industries, like, image recognition, speech recognition, text recognition, where classification is very important. But in economics, classification is actually a bit less important, in the sense that people work a lot with continuous variables, and so it's more imperative to learn things like regularized regression, right? Lasso, Ridge, whatever, that help you work with continuous variables such as GDP growth, inflation, etc. Right? There is obviously scope for classification, but it's not as kind of prevalent as in typical machine learning boot camps. And so there is a lot of work to kind of, adapt all this standard material to a particular domain, which I selfishly wish would have been done by somebody so I could just follow.
Is there something that exists already, at least partially, that you think you could leverage on?
Well, so the only kind of way is to you leverage on the theoretical material from existing statistical learning books, right? But then it's up to you to kind of see what's happening in the literature and go out there and find all the data sets, which is not that easy because a lot of the applications they are cross-sectional in nature, meaning that you're looking at the data that's snapshot of a group of people at a point in time, right? And in economics, it's actually those kind of data tend to be very proprietary and very expensive to acquire. And so, yeah, this is a kind of a constant struggle to see, how to provide motivating examples for students, which means that you have to go and, read the literature very aggressively and follow up on any data sets that come out of that literature.
So you have trouble not only with the reference material, but also with the raw data that you could actually use within your classes.
Oh, I think the data is the biggest problem.
Biggest problems.
Yeah. Relevant data.
I think data analytics, data science, AI, machine learning is a general purpose tool. So it cuts across discipline. So I have the same challenge. But there isn't enough resources for verticals. And even if there is, it may not be purpose fit. That's why there's room for us to develop materials to serve specific target, which is a good thing. But the challenge is that you have to basically, look through the literature, get the data, and come up with a good use case that would resonate with the most people.
Yeah, I would agree that a domain-specific textbook will be very useful. It's called machine learning for business students. That doesn't exist. What does exist, however, are hundreds, maybe thousands of articles in outfits like Harvard Business Review that are usually very positivist and very unbalanced, and are usually out of date already after 1 year. So I think that's a bit of a challenge because, you want to keep up with the technology, so you have to read up on the latest developments. But at the same time, you don't just want to repeat all the hyperbole that's already out there. You kind of want to take an independent and stance. And I think that's something that just doesn't exist, not in a business world and probably not anywhere else.
So do you feel that we need this platform? Perhaps with so many of us working on AI-related material, perhaps we could pool our resources, at least in terms of the data, which is one of the things we're striving to work towards, which is this common pool of resources, not only content for your modules, but data sets as well. I think it's something we'll start to move forward with.
I was having a discussion with Colleen. So you guys are building a skeleton, right? So I think it would be cool if with that skeleton, we build the muscles. Then we have something complete.
We can.
Okay, I just want to amplify the point raised by the other panelists. So I think it's important for us to build out a common pool of data for teaching students. And not just about good quality data, but good quality data, they are organized by vertical domains. Because a lot of time we find ourselves when we teach specialized topic, right? We just couldn't find the right data sets on Kaggle or from anywhere else. So I think this platform offered by Rosetta will be very useful.
Yes, I also agree that a common data pool is very important. And yeah, as mentioned, the other thing is that I wish I can have get students to work on bigger scale projects. Like when I look at my teaching feedback, there are some portion of students might say that okay, they think what they have learned in the module is not applicable enough in the future. So probably because the question that they have in their homework assessment is too small scale. So that makes them think that, okay, it is not related to real life. So yeah, if I can get them to work on bigger scale project, that might makes them think that the knowledge they have learned in the module is related to their real life application.
So actually, to come back to business, there is actually one book that kind of comes close called Data Science for Business by Matt Taddy, who is the chief machine learning scientist at Amazon. But even there, you can see the kind of hardship because he also kind of cheating by using data sets that comes from mainstream machine learning literature, like, shards of glass from the CSI investigations and so on. And partly the reason is because even though he is, chief ML person at Amazon, Amazon wouldn't let him use Amazon data to provide examples because, they treat their data very seriously. And so he is still forced to illustrate some of the machine learning algorithms with, non-economic, non-business examples.
Okay, perhaps if no one else has anything to add, I'll have a look at some of these questions that are on Padlet, and I'll open them to anyone who wishes to answer them. So I guess the first question we sort of answered again, but we can reiterate. Do you teach students coding? Why and why not? In an AI-related module, do you teach your students coding? Why and why not? Andreas, maybe you can answer this since your students don't do it.
The simple answer is no, I don't.
But why not? Or is it just not necessary?
But it's for the objectives, it's not necessary. They can understand AI in a business context without having to code. I mean, there's this perception that sometimes also that you can read in business magazines that now every executive needs to learn how to code. I think you can really understand AI very, very well without actual coding. That's kind of what I'm trying to do.
So I guess it depends on the kind of student that you have, right? So if the students don't need to code in the end, then you shouldn't really have to force them to learn how to code. Right? It depends on what you want them to do with the content you're teaching.
One thing I would like to add is that even though they do not code, it might be good for them to get exposed to coding so that they develop empathy towards their coders. After all, if they want to deploy or come up with AI solutions, they need to work with the computer engineers, the computer scientists. They need to know their pain points, their challenges. So once you develop that empathy, I think team dynamics is going to be a little better. That's my personal view.
So having a better understanding of your entire team based on, it's like sharing, like going through all the different tasks in your, yeah. That's a good point too. So another question here. So I think it's a similar question. I'm teaching AI for non-CS students. I feel students are excited to learn AI algorithms, but they don't like to code. Do they actually need to know the implementation of ML algorithms? So maybe going back to your point on, okay, they can understand the pain points, but do they need to know the algorithms themselves? Is coding enough at a basic level?
Okay, so maybe I can answer that. So I think these days students are very happy campers because a lot of these algorithms have actually been successfully packaged into very easy to use higher level packages. So, students do not need to code like gradient boosting algorithm itself, like from scratch, right? That's kind of where the pain is. So when teaching like, machine learning for economists or this kind of class, right? I teach them enough to get the results, right? And to tweak the analysis, maybe, do some data cleaning, which is all really basic coding, right? There is nothing special about it. Basically, for loops and all that. So I think the coding component of the class, right, is really driven by the learning outcome. So we're not teaching coding for the purpose of teaching people coding. Right? I always ask a question, okay, you want to code what? Right? Because coding can be applied to so many. We were looking at robots, right, this afternoon, and coding stuff for a robot requires a very different, subroutine knowledge and stuff than coding, a linear regression or a machine learning algorithm. And furthermore, nowadays R and Python have a lot of tools are ready to deploy. And you just need to know the key tuning parameters and how to do cross validation on those, etc. And so actually, I think these days are very happy days for students who want to dabble into machine learning, right, with some domain knowledge, and don't need to have this kind of hardcore CS background for writing, highly efficient, foolproof code. So I think actually we live in a very good times for, and this is why perhaps machine learning exploded so much across disciplines, because I may be completely wrong, but like 20 years ago, the chief role of the data scientist was to actually implement algorithms without thinking too much what are they being used for. Whereas now that we have these very cheap to use tools in open source languages, the focus has shifted into what kind of domain questions we can actually answer using those algorithms. And this is where, at least in my case, the learning outcomes of the course come in.
Yeah, just to add on, I think data science has been democratized. So much so that in the past, you need 100 of lines with C++ to implement. Right now, you just need one line with Python. Using some packages, you can have all the popular methods throwing all the actionable insights. So this goes back to, do you want to climb the mountain or do you want to just focus on the skiing? So if the students want to focus on the skiing, give them that. But maybe as they ski, they may develop some appreciation over the mountain climbing. Then they can deep dive. But for those who just want to apply, why not? Just let them ski.
Maybe just add on another little on the point that I mentioned earlier on this topic. For college, we actually face this scenario, right? I would strongly recommend them to consider using a no-code visual tool. Why is that so? Because when you use a no-code visual tool, the degree of conceptual understanding that you need on machine learning itself is actually the same as programming. But the nice thing is that you don't really even need to write one line of code. So you can actually focus on the conceptual understandings to get yourself familiarized before you decide whether you want to learn programming to do a little bit more.
So that's to elaborate what you're saying is, if you're only addressing the application,
Yes,
like
or
the
non-CS
usage,
background student.
Yeah.
Right. That would be very helpful.
they don't have to delve into the algorithm, so it's not important to actually implement it.
Yes,
Yeah.
yes. But they will have a very good conceptual understanding of how to use the model, how to evaluate the model, and how to deploy the model.
Okay. So it would be cool for you to have a line that says you know Python and you know how to deploy AI, versus you know how to do virtual tool that is not often used by the industry. So I think it has market positioning indication.
But I think there is an interesting trend here that I would like to mention, and not sure if you have come across this in your teaching. It's also ML. So firms like Data Robots that now offer tools where they claim that you can give this to a normal kind of business analyst in your firm and can let them build machine learning models without writing a single line of code. I think that's very intriguing to me because I might thinking if I might at some point use that in my teaching. As of now, I don't really see a way to do that because these are commercial tools, so you would need to buy a license. But if there's a way to perhaps build something similar, maybe like a simpler version that can be offered to education institutions, similar to these auto ML techniques, I think that would be extremely interesting, and that might find many applications, especially in business schools and in other non-CS departments.
I think some of the libraries do include AutoML components in them already. You could try to have a look, but that would mean that your students would have to delve into code. Unfortunately, yeah, it's not a plugin. Yeah.
I think what I have in mind is really, and I think what Data Robot offers, according to their marketing material, is really, developing without any coding, just drag and drop, with simple commands.
GUI, just
a GUI, exactly. Yeah, like a self-explanatory tool. So I think if that comes to fruition and if that sort of develops and spreads more widely, then maybe there's a way to also include that in education.
Yeah. Okay. So for me, right, my module is to the main objective of my module is to use computer to solve mathematical problem. So yes, implementation is quite important in my module. Actually, I would ask students to code out like simple things like matrix multiplications, and I also ask them to compare their implementation with the existing libraries. So of course, they will find that the existing routine is much more efficient, but the important point is that if they have special case like special metrics, can they modify their implementation so that their implementation will be much efficient compared to the standard libraries which solve general cases. Yeah, so I think that's the important point.
I would like to add one thing. So I think one thing with democratization of AI and data science is that, we do not want people to anyhow deploy AI because there is an issue of AI ethics, AI fairness. So, using off-the-shelf solution and comparing it with one solution where you can control for fairness, this allows us to teach students, AI affects people's life potentially. For example, in the context of financial institution, whether you lend to a person or not, whether a person can be insured or not. If you automate that, and AI is systematically biasing against a certain group of people, this is affecting people's life. So, this is something that I think, especially in business school, we are concerned about, right? So the person who learned about AI do not need to learn how to code per se, but at least he needs to understand when he works with, let's say, the computer engineers, this is the kind of issue that they need to, get a hang of.
Proper testing. Yes. Okay, so perhaps we will move on to one last question. So this question, just let me read it out. Many of you emphasize teaching the application of AI. I wonder how you teach it so students learn to deal with new situations. So this is the problem-solving component within AI. How do you actually leverage AI in a problem-solving, general problem-solving kind of context? And do you actually teach this within your modules? VK?
Okay, so if I understood the question correctly, right? I think the important thing here is always to focus on the basic idea of problem solving, right? So one of the unique things that I normally teach in my machine learning course is that we teach a proper methodology on solving problem. So for example, we use things like CRISP-DM. So by using CRISP-DM, we actually try to get the student to identify a problem around them that they want to solve with AI or machine learning. And then we walk them through each step of the process. And if you're familiar with CRISP-DM, you know that CRISP-DM actually start off by talking about the business objective of this thing. So it helps to put it in perspective on what they should do in the subsequent stages of machine learning. So we keep them focused on solving the problem itself instead of getting lost in a data-driven approach. Yeah, so that's something useful to look at.
Does that mean it's not tied to data? Is that what you're saying? It's not tied to, let's say, a supervised learning problem?
No. We actually start with the problem first. So once you identify the problem, you then ask yourself, what sort of data can answer that question within your organization or in your surrounding? And then from there, you choose the right algorithm to do it. So always anchor back on the problem solving approach to make sure that they are focused on the problem and less so on the data and the algorithm.
So what happens if the data they've identified is associated with a model that you don't teach?
Okay, so that is where we have peer learning. Remember, I talked about the peer suggestion early on. So sometimes the peers can come in and give you a different perspective on how to work with the data. And our side, we also conduct small group consultation with the student. So if this then is not covered in our topic, as usual, students like to use bombastic things that we don't cover in our teaching. That's a reality that I notice. So we try to go teach coach and through one-on-one consultations to solve this problem. Yeah.
Anyone else?
So one mindset that I hope to instill among the students is the product mindset. So what I mean by that is that whatever you have learned, try to productize it. So that means they will be proactively looking for problems to solve. How do they solve that? Either with what I have taught or with anything they have come across in other modules. but it's a mindset about turning something that you know, you have learned, into something that you can sell. Product. So this allows them to actively look for use cases, be it AI, be it whatever data analytical tools they have picked up.
Right. So actually, all of the problems are very similar, right? So they say, oh, it's a different problem, but at the end of the day, at least, for economics, right, there is two kind of very broad problems. One is a problem of prediction of, what is going to be the value of the variable, say tomorrow, right? What's going to be inflation 1 year from now, right? So that's kind of the non-causal prediction, right? I use whatever the data I can to just make that guess, and I'm happy if I'm right, but I don't know why, right? It's not like, I looked at some variables and I claim that they caused inflation to rise. And then there is the question of causal prediction, right, where it's of interest to policymakers. Say, well, if I change my interest rate by this much, what's going to be the change in inflation, right? So these are fundamentally kind of two different problems. My course focuses on the easier problem, right, the non-causal prediction, because that's where most of the supervised machine learning algorithms is very well suited to deal with. Right. And I spend a lot of time at the beginning of the class to explain just the general prediction problem to students. How, it's actually like similar to a decision-making problem. So we have the primitives, we have the data, right, which forms the predictive distribution. We have the loss function that is determined by our organization or, the particular question we're trying to answer, right? And then those usually give us optimal forecasting rule, right? If we're using the squared loss, right? Willing to be agnostic about, which error is more important, then, the optimal predictor is the conditional average, right, of the predictive distribution. And then all of the methods are basically trying to estimate it from the data, right? And so whatever algorithm you use, right, you're doing the same problem. And so it's just different approaches to the same problem that we teach. And so if I don't teach one particular esoteric variant of that, well, once they have the structure in their head that this is what I'm doing, right? And another kind of helpful analogy is, I think it was Francis Diebold, one of the econometrics people, but I'm sure there were many variations of that. There's basically this version of supervised machine learning in one slide. There's basically just a few general lines, basically tell you, okay, you're maximizing an objective function subject to a penalty, blah, 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 with a loss function of a particular form. And then after every lecture, after I teach every algorithm, I pull up the slide and I say, okay, in what we learned today, what is the objective function? What is the penalty? What is the parameter that determines the strength of the penalty? What is the loss function? And then students gain this understanding that even though what they're doing seems very different, at the core, right, the objective is exactly the same. And so whenever they go out, right, and they learn a new method about, predicting y using variables x, they hopefully have this understanding that, okay, this is just another kind of trick to get the estimate of the conditional mean of the predictive distribution, right? Just using a more flexible functional form or a different regularization device. And I think once, you kind of instill that understanding, then they can do and they can solve problems, which seem different, but actually not that different at the core.
What about the other kind of problem you're trying to solve? Not the predictive one, but the descriptive one.
Well, it's not descriptive. It's still predictive, but the difference is causality.
Yeah.
Right. That is a much more difficult problem because then you first need to have a background in causal inference and strategies of identifying causal effects. So that brings you to at least one more class in causal inference in econometrics. And then you can have another class where you can try to see where machine learning can come in to enhance. So nowadays there are popular terms like double machine learning, right, or causal machine learning that companies such as Amazon emphasize a lot. At the moment, a lot of that stuff is done by PhD training. So it's a little bit a higher barrier to entry because you first need to have a good background in causal inference itself before you can try to see how ML make your life easier there.
Does anyone else have anything to add? Especially in terms of relating any models you generate in an automated fashion to, real or existing models, just to validate.
I'll abuse the time then. So, actually, right, there is this no free lunch theorem, right, that says that no method is always the best. And so when we should be careful talking about models, right, because when we say a model, it implies some kind of prescriptive way. As we're saying that these variables determine how this other variable behaves, right, and that's kind of giving it the causal. So I think predictive approaches or something like that would be safer terminology. And so what I teach students also, right, when I show them the applications, I'm saying, okay, we applied these few methods and we see different results. Why do we see them? Well, that's because of the underlying data, right? Because if the predictors were very well correlated, then something like dimension reduction via principal components would work very well, right? But here we don't have that, so we see that we cannot use that technique, right? And so each method works better in a particular situation, right? And when they have the appreciation for that, then when they look at the result, they can rationalize the results. And even before what I teach them, I say, okay, look at this problem and tell me, out of these methods, which one will be the worst before you even run anything on your computer, right? And oftentimes you can do that by just looking at the data and knowing, when particular methods do well and when particular methods don't, right? So I think these are the aspects that are important to convey.
Anyone else with any final comments?
I think that's a very good point highlighted. So I think I just want to maybe end this by highlighting that's one of the reasons why we never talk about auto ML in our teaching. Because when you talk about auto ML, students will have the notion that you pun your data, you get a good model without understanding why that model is good to begin with. So even though we are using no code visual AI tool, we always refrain from going into auto ML in those tools. Yeah.
Okay, perhaps I don't have any new questions, so I would like to thank all our panelists and then you, the audience, for asking all of these questions. So yeah, I think that will be the end of this panel session. Thank you so much.
Thank you, everybody. Thank you. Okay, so that brings us to the end of our program today. So in the form, we've asked you whether you're interested to join Rosetta, and we've gotten actually very, very encouraging response. We had about 115 people registering, and about 70 plus are interested in joining Rosetta. So that's very, very encouraging. Now, as I was mentioning to my teammates a couple of days ago, right, this is just the beginning. So from here on is when the hard work really, really starts. Okay, so we will get in touch with you for those of you who have indicated interest, and we will actually start working out programs that we're gonna do, right, in order to really have move forward with this initiative. Okay, so once again, thank you everybody for coming. Also like to thank my team, Darren, Wikek, Akshay, Amir is gone already. Amir was here most of the day. Yeah, as well as my student helpers. They're waving through the window. Yeah, some of my student helpers. So I'd like to thank all of you. I think, and most of all, I'd like to thank all of you for coming, especially those of you who are here, as well as those of you who are online as well. Without your presence here, right, then there's really not a lot of point in doing this. Okay, but we've had all of you here. It's really been it's great. Okay, of course, I'd like to thank Zikai also, our live stream specialist, as well as Philip, who's helping us to ensure that all these microphones and all work. Okay, and Chris, yeah, as well as Chris. You can't see Chris. Chris is behind the camera. Okay, so thank you everybody, and we'll get in touch again with you. Okay, so thank you and have a good day.